Hello and welcome. In this video I'm going to show how to solve a basic conditional probability problem. I'm going to show how to solve it in 4 different ways. The ways are related, but as you'll see, they sort of will run the gamut from being very sort of computation and formula intensive to being essentially like very sort of pithy and and concise. Okay, so here's the problem. You have 3 cards. The first card is green on both sides. The second card is red on both sides. And the third card is green on one side and red on the other. So in our little scenario here, the cards are going to get mixed up, shuffled if you will, or mix up in a mystery box. And what you're going to do is you're going to select one of the cards, but you only get to observe one side of the card. So you pick the card and whatever side is up you get to see. Okay, you observe green. So the question is, what is the probability that the other side is green? So if you just want to test whether you know how to solve this kind of problem, what you should do is pause the video now, work through the problem, and see what answer you get. Okay, so like a common intuition for this problem is to say, well, I think the answer is a half. And the reasoning for this, someone might say something like, well, there are 2 cards that could possibly show a green face when you draw them. One of these cards is green on the other side, and the other card isn't. So if if one card out of the 2 has green on the other side, then the probability that the other side is green should be a half. Okay, this is not correct. This thinking is folly. And so I'm going to show 4 ways to arrive at the correct probability that the other side is green, which is 2/3. And I'm not going to do a simulation in this video, maybe in a later video. Okay, so these are the methods. I guess you could call this like the 4th method. Okay. The first is to use Bayes' theorem, and I consider this to be a sort of brute force approach. Secondly, you could use the definition of conditional probability, and when I do that, you'll see that it's almost the same thing as just using Bayes' theorem. You end up in a very similar boat, but like the path that you take to get there is different. Thirdly, you could use what I call the Bayes trick. And if you have experience using these doing this sort of problem, you can see that this trick will work. And fourthly, there's the tree diagram trick, which is the most concise of all of the methods. Okay, so the first thing you want to do is build a tree diagram that represents the problem. Now, in the last 24 hours, I've made a complete sort of flip from thinking building a tree diagram is stupid and needlessly complicated to basically feeling like a tree diagram in these kind of problems is absolutely your best friend. And the reason that I've made this flip is because once you've built the tree diagram, you can basically just choose which one of these methods you use, I guess depending on like what kind of mood you're in, or more importantly, potentially, is what you're specifically being asked to do. So you could get a problem, a conditional probability problem that says solve using Bayes' theorem. You could get you get a problem where you're asked to specifically use the definition of conditional probability, or it might be unspecified, and in the interest of time, you might just want to use the most efficient method. Okay, so how do you build this tree diagram? You have to determine what your variables are. So in this problem, you've mixed up the cards and you're going to draw a card. So your first sort of random variable, if you will, is which card you select. And that can be card 1, 2, or 3. And secondly, there's going to be a color on the face that you see. In this case, we know that it's green, but I want to point out that like this is also a random variable, right? It could be red or it could be green. In our problem, it's green, but it could be either. Okay, so just recapping here. This is how you build the tree diagram. You start with like a primary node, and then you build a branch, and the branch basically represents the outcomes of your highest level random variable on the hierarchy, or like you could call it like the first thing that happens. So you could get card 1, you could get card 2, or you could get card 3. The next thing you want to do is at the end of that node, and this is just my convention for doing this, I like to, along the branch, I like to write what the outcome is, and at the end of the branch, I like to write what the probability is of that happening. Okay, so you've got your first node here. Okay, so supposing that you've selected card 1, there's two things that could okay, in theory, once you've selected a card, there's two things that could happen. You could see red or you could see green. So each of these nodes will form 2 more branches. Red and green for each one. Now, we're given a whole lot of information about the cards. So you know that once you've arrived at the first node, the probability of seeing red is actually 0. The probability of seeing green, if you've drawn the first card, is 1. And so it goes for the other cards. If you've got card 2, the probability of red is 1, because card 1 is red on both. Card 2 is red on both sides, green on none of the sides, and card 3, you've got a 50% chance of seeing red and a 50% chance of seeing green. Okay, and what I have here is just a little adjunct to this, and I call this coding the nodes. Okay, so node 0 is our primary node. Node 1 is going to be the outcome of the first random variable, and node 2 is the outcome of the second random variable. In other words, node 1 is what's called the prior distribution of the card variable, and node 2 represents the conditional distribution of color given your selection of card. Okay? Moving on, I think we're making pretty good time here. Okay, so before we use Bayes' theorem, we have to sort of see through a little bit of bullshit here. In this problem, the business about the probability that the other side is green is, in a way, a red herring. And I want to note the similarity between this and the switch variable. If you watch my video on Monty Hall, basically I say that this business of whether to switch or not shouldn't explicitly enter into your equation. Rather, it's like a consequence of getting posterior distribution. So I point out that the important question is, what is the posterior probability of card given your evidence, or in this case, given that you have a green face showing? Okay, since the color identities of the cards is defined for us, a probability statement about which card you hold is equivalent to the probability of flipping to reveal a certain color. Okay, so we are going to use Bayes' theorem. If you don't know what Bayes' theorem is, you should stop. You should write it down. And you should see that all I'm going to do in the next few steps is basically plug in the specifics of our problem into Bayes' theorem. Okay, so right here I'm showing the posterior probability of card 1 given that the color we've observed is green. And by Bayes' theorem, that's equal to the probability that the color is green given card 1 times the probability of card 1 divided by all of the different ways that you could have seen green, which is the probability of color green given card 1, probability of card 1, notice that that's the same piece as is in the numerator, plus all of the other ways that you could have seen green. Okay, so we're going to go through, and the beauty of building the tree diagram is that once it's built, determining these conditional probabilities is very easy. In fact, it's just a matter of sort of multiplying along the branches of the tree. So the probability of color, that the color is green given card 1 times the probability of card 1, all we would do is grab the probability of card 1, which is this piece, which is 1, sorry, is 1/3, times the probability of green given card 1, which is 1. Okay, so we would get 1 times 1/3, and then in the denominator we would get the same thing repeated once, plus the probability of green given card 2 times the probability of card 2. Probability of card 2 is 1/3. Probability of green is 0. 1/3 times 0 is 0. And then we would take the probability, so there should be a plus here, the probability that the color equals green given card 3 times probability of card 3. Probability of card 3, 1/3 times probability of green given card 3, which is a half. So we would get 1/3 times a half. And so now it's just a matter of chugging through this thing. You can notice that the 1/3s are all going to cancel. And so you're just going to be left with 1/1 plus a half, which is 1/3/2, which is 1 times 2/3, which is equal to 2/3. Now, as a little spoiler, that's the answer. You're technically done, but I want to proceed and actually calculate the entire posterior distribution of card number, just to show that you know, it's doable. In this problem, it's not informative, but it might be in other problems. Right, so you would just follow through with the same thing, except now you're substituting card 2 in here. Okay, I guess I should be a bit more articulate. The reason why you might want to do this is the problem could ask you to calculate the posterior distribution of the card that you've selected, in which case it's essential that you understand that doing that involves computing the Bayes theorem probability for not just one event, but for all possibilities of that first random variable of which card you select. Okay, so we would go through, we would do a similar thing here. Using our tree diagram, the probability of card 2 is 1/3 times, what's the probability of a green card given that you've drawn card 2? Well, that's 0, so we have 0 in the numerator here, so this whole term becomes 0. And then in our third scenario, the probability of green given that you've drawn card 3 times the probability of card 3, okay, well that's 1/3 times a half. And the denominator term is going to be the same as on the last page. So in this case, we would just get 1/3 times a half. Okay, well, you know, you can write this out. You can do your cancellation of these 1/3s, and you can see that you're left with 1/2 now over 3/2, which is equal to 1/3. So basically, we're done. We've used Bayes' theorem to solve this problem. It's just a matter of sort of putting into practice what I mentioned before, that this flipping business is kind of a little bit misleading, because basically the probability of flipping to reveal a green is equivalent to the posterior probability of having card 1. The reason being, like, we know card 2 is off the table. Okay, we know that if we had drawn card 3 and we flip it, it has to be red. So that's not an event that we're interested in because we've seen green. Okay? So the posterior probability of drawing card 1, as we've calculated on the last slide, is 2/3, which is the correct final answer. Okay, but how else could we have done this? Well, we could have used the definition of conditional probability, which is the probability of A given B is equal to the probability of A and B that is the probability of the intersection of A and B, or as I'll often call it, just probability AB over the probability of B, the marginal probability of B. So to do this calculation, then you would have to know what the joint distribution is of color and card selection. So how do we get at that? Well, notice that you could swing this guy out here, basically multiply both sides by the probability of green to say something like the probability of color given green times the probability of green is equal to the joint probabilities of color and green. But since and is symmetric, we know that that's also equal to the probability of green given color times the probability of color. Now this should look very familiar because this is exactly what we did using Bayes' theorem. Okay, secondly, you want to make a table that represents the joint distribution. Okay, and to do that, we use this relationship right here. And this, again, is just multiplying along the branches of our tree diagram. So red and card 1, we would get 1 times 0, which is 0. Green and card 1, 1/3 times 1 is 1/3, and so forth. And you can complete this table. And what you're looking at right here, oops, that was a really bad square. Pretend that didn't happen. This piece right here is what's called the joint distribution of red and green. Okay, thirdly, we have to compute the marginal probabilities of color, or really we only have to do the marginal probability of green, but just to show you that all of this information is sitting right here in this table, all you would do is sum along columns to get the marginal distribution of color, or you could sum along the rows to get the marginal distribution of card, but we already know what that is. So we sum 2/6 plus 1/6 is equal to 3/6. Okay, and now we're ready to compute. The probability that we drew the first card, given that we've seen green, is equal to the probability of card 1 and green divided by the marginal probability of green, which is equal to, well, 1 and green is 1/3, divided by the marginal probability of green, which is 1/2. 1/3 over 1/2 is 2/3. And so keeping in mind my last point on the last slide, that once you know the probability that you're holding a particular card, the probability of flipping it to see a certain color is implied in that. You can see that we are done and we have computed the probability that we are asked for. Okay, so this is using conditional probability. Okay, this method I really like because it shows not just that you know what Bayes' theorem is in very technical detail, like you've looked it up in a book and you can like explicitly copy the formula. You know, this shows that you have a sense of like the relationship that Bayes' theorem is actually suggesting, sort of more generally. So this is like a little bit less rigorous, it's fast, but if you were asked to use Bayes' theorem to do this computation, if I was grading the test, I would give this not just credit, I might give it like an extra point, because I think this is like a pretty hip way to do it. So notice that the posterior is the likelihood times the prior over some constant. And as you could see when we did the brute force Bayes' theorem computation, the piece that was in the denominator for each element of the posterior distribution was the same. It was the same summation. It was the total probability of green over all the cards. So you can say that the posterior is proportional to the likelihood times the prior. And this is the constant of proportionality then would just be, 1 over c, or c, depending on which side of the equation you put it on. Now, if the priors are all equiprobable, which they are in this problem, because the probability of drawing each card initially was 1/3, they will cancel out of the equation, and you can state that the posterior is just proportional to the likelihood. Okay, this becomes very easy to hash through for each element of the posterior distribution. So the probability of 1 given green is proportional to the probability of green given 1, and we know that that is equal to 1. The probability of card 2 given green is proportional to the probability of green given card 2, which we know is 0. Oh, and again, you know, to extract this piece, you're really just looking at what's happening at the very end node here. So this use node 2. And then the probability of the third card given green is proportional to the probability of green given the third card, which is equal to a half. So now you've got like 1, 0, and a half. The next trick is to quote-unquote normalize these so that they sum to 1, because we want you know, we want standard probabilities here, so it has to be, you know, a non-negative number less than or equal to 1, and for the entire sample space it should sum to 1. So all you do is you multiply each one of these guys by x, and you set that equal to 1. Okay? You solve for x, and we get that x equals 2/3, and then we just back substitute that in to get the normalized probabilities of each of the events that we're talking about. So in this case, the probability of card 1 given green is equal to 1, what we calculated here, times this this normalizing factor of 2/3, and that gives us our final answer of 2/3. So you can see that this is kind of a slightly slicker way to do the problem. I think it is anyway. Okay. What's going on here? Okay, and then there's the tree trick, which uses some similar ideas to the last problem, but this is like if you need to do one of these problems really quick, I don't know, there's 3 minutes left in the exam and you're like, oh, I didn't do that conditional probability problem. Here's a way that you can do it. You build your tree, and basically you just multiply along the tree the probabilities for each node 2 that matches the evidence. So the evidence is that the card was green. So basically we care about this node, and we care about this node. Okay, I mean you could include this one, but okay, so then you do your multiplication along here. 1/3 times 1 would give you a third. 1/3 times a half would give you a sixth. I mean, we could include 0 in here as well. Then you use the same normalization trick that I showed on the last slide, because you want this represents sort of like a ratio of like where the mass is, if you will, in this discrete distribution, like the proportional masses associated with each of these outcomes. You do your little normalization trick, right? So you get a third x plus a 6x plus 0x. You would solve for x just by combining. Half x equals 1, x equals 2, and then again you could just back substitute in or multiply each one of these numbers by that factor you've come up with to arrive at your answer. So if you can sort of if you know that this is really the event that you're interested in, then like if you can see through the problem well enough to know that like this is really the piece that you're after, once you multiply along to this piece and then you solve for your proportionality, your normalizing constant, then it's really just a matter of multiplying what you get times your number here to get 2/3, which is the answer. Okay, I hope this has been helpful to some people. I know it was helpful for myself to see that there are sort of different ways to think about the problem, and that there's sort of a spectrum of how much you want to involve memorization of formulas, how much you want to utilize, like, quote, tricks, how much you want to utilize definitions, whether you want to bother constructing that table of the joint and marginal probabilities. Basically, you have a lot of choices, and all of these different methods will lead you to the same answer, provided you've seen the problem for what it is. Okay, thank you very much.